much for making the time to try this and record some of our history. I was thinking that for the first interview, we can start from the time or close to the time that you came to Michigan, and talk about this, and then take it from there.
Well, my introduction to University of Michigan came as a result of my department head at Michigan Technological University. I had gone to Michigan Tech as a lecturer with only a master's degree, and the department head at Michigan Tech was a good friend of Frank Richart. Frank, we'll call him Bill from now on, simply because he was a junior and didn't want to be called junior, so his mother called him Bill. In any case, Bill Richart and GeorgeYoung were friends from graduate school at University of Illinois. And GeorgeYoung told Bill Richart about my performance at Michigan Tech in teaching courses there. And so Richart had me come down to Ann Arbor for an interview, at which time he offered me a National Science Foundation Fellowship. They were the primary engineering outcome of Sputnik, the United States attempting to catch up to the Russians. So I accepted the fellowship, and after only 1 year at Michigan Tech, I came to Ann Arbor in 1964. By coincidence, or maybe by design, I'm not real sure, VincentDrnevich was also starting his PhD with Bill Richart in the fall of 1964. Vince and I had overlapped at Notre Dame. When I was doing my master's, he was finishing up his baccalaureate degree. But once again, then we were together working for Bill Richart in the so-called new discipline or sub-discipline of soil dynamics. At that time, on the faculty at Michigan was JohnRHall, Jack Hall, who became a co-author on the textbook that we wrote in soil dynamics. In addition, on finishing his PhD in those years was JohnLysmer. John graduated in, I believe, 1965 and moved on to University of California, Berkeley, where he completed his academic career. So Vince and I immersed ourselves in learning from Jack Hall and Bill Richart where the subdiscipline of soil dynamics was at that time. It was in its infancy. The other school that was doing similar work in soil dynamics was MIT with RobertWhitman. Whitman and Richart collaborated on some publications and in some research.
Did you know that you would be working on soil dynamics when you came?
Yes, that was made clear in my interview with Professor Richart.
What did you think?
Pardon me?
What did you think of it when you heard it, like as a topic, you know?
Well, actually, I was quite familiar with it because after my master's at Notre Dame in 1962, I went to work for the Air Force Weapons Lab in Albuquerque, New Mexico. And I was a civilian employee of the Air Force, but our task was to design underground protective structures in tunnels and shafts. Of course, read into that ICBMs. I was quite aware of the need for knowledge of soil properties to make predictions on cratering and bomb effects. But I at that time did not realize or understand the more industrial applications of soil dynamics, which then I followed through the rest of my career, as a matter of fact. My own thesis was devoted to determining the effectiveness of trenches, open trenches, in mitigating the amplitude of Raleigh wave vibrations at the ground level. There had been, as far as I could tell at that time, only very few attempts at screening or mitigating ground vibrations, and they had been performed in Berlin in attempting to reduce the vibrations from the subway to printing operations. At that, in that era, color printing was, while quite widely used, still requiring very low, small amplitude sites, vibration sites. So the subway running by the printing plant caused problems, and a man by the name of Dahling in Berlin devised a slit trench in which he filled with a bentonite slurry. And this worked beautifully for several days or maybe several weeks, after which the slurry hardened and became a more or less rigid gel. And that ruined the isolation effects. Well, I picked up on that research and concluded that you should not fill the trench with anything. But that becomes a problem too in making a deep trench which is empty. You have to have something to hold the sides back. In any case, my thesis was devoted at determining the effectiveness of open trenches with no filling. And as far as I know, that was the most extensive experimental program looking at that particular problem. At my graduation with the PhD at Michigan, I was offered a job to stay on the faculty. Professor Richart enticed me to stay by offering me the co-authorship of a textbook which was imminent. In preparation for writing the textbook, we offered a short course at the University of Michigan, a summer short course on soil dynamics, and we enhanced our lecture notes for that short course, and the lecture notes became the basis for the textbook. And so Professor Bill Richart and that time Assistant Professor JohnRHall and myself as Assistant Professor collaborated in writing the textbook Vibrations of Soils and Foundations. That was published in 1970. It still remains about the only basic text on soil dynamics and a good place to start.
Yeah.
I've having joined the faculty.
So when was that? When did you join the faculty?
1967.
67.
And at that time, the University of Michigan, Caltech, Berkeley, Columbia, and maybe some other universities, as a consortium, agreed to support the startup of a new IIT, Indian Institute of Technology, in Kanpur, India. And during that startup phase, each school was encouraging faculty to spend some time at Kanpur. Also at that time, we had a collaboration with the University of Karlsruhe in Germany, particularly Professor Bernd Prange. And he was attempting to learn what University of Michigan was doing with resonant column testing in particular. And so he sent one of his students, WolfgangHaupt, to Michigan to study with Bill Richart. So in the summer of 1969, Haupt and I worked together, he expanding his scope somewhat to look at isolation problems. The department was at the same time trying to recruit people to go to Kanpur. So in the conversations about those two issues, it turned out that I got an offer from Karlsruhe for me to spend a semester at Karlsruhe, but on the way I would spend the summer at IIT Kanpur. So in the summer of 1970, I took my first round-the-world trip, traveling first to Japan, and then a short stay in Bangkok, Thailand, at which time I found our textbook already reprinted in paperback with no acknowledgement of our publisher.
Wow.
But that was the expectation in those days. Your book would be published quickly. And of course it was in Chinese. So I bought a copy, not being able to understand anything but the figures. In any case, then I went on to Kanpur, India, and introduced them into some of the things that I had learned in isolation of vibrations by trenches, and taught them how to perform cross-hole seismic tests. That reminds me of another important development during those years. We had a young graduate student who was assigned to me as he was doing his master's study in soil dynamics as an assistant. His name was Kenneth Stokoe. And in the preparation of his coursework at Michigan, Bill Richart felt that he ought to have some other experience with different faculty members, and that, well, of course, Bill Richart was an Illinois graduate, and he said, well, Stokoe, you ought to travel to Illinois on the Big Ten Traveling Scholarship Program, which Stokoe did. Stokoe continued to work for me at various stages on my thesis, on the, particularly the field experiments at that time. But when Stokoe came back after a semester at Illinois, he had this idea of cross-hole seismic testing, which he learned from the geophysics group at Illinois. And so we began to examine the cross-hole technique, and I used it for characterizing the soils at my field site. And that led to a collaboration with Stokoe after he got his PhD in developing the cross-hole as an important tool for characterizing dynamic properties of soil. That turned out to be an important tool in design of nuclear power plants and other large structures in seismically active regions of the world. So after my summer in Kanpur, where I started a long-term friendship with ProfessorYudhbir, which I still maintain to this day, I moved on to Karlsruhe for a semester, the autumn semester of 1970, where I worked with Haupt, and he chose for his thesis topic at Karlsruhe also isolation by barriers. Now, barriers this time including filled trenches. And his primary medium was Portland cement concrete. He built a facility very much like the one that I constructed at Michigan in the laboratory in Karlsruhe. And he and I then performed experiments with various isolation techniques throughout the semester that I spent in Karlsruhe. And at the end of that semester, I was invited back again. I came back to Michigan for a semester and went to Germany again and worked another semester with Haupt on his isolation tests. During that time, we examined and used for his experiments cross-hole testing, but also the very rudimentary Rayleigh wave testing, Rayleigh wave dispersion. Rayleigh waves travel at different speeds in different soil types and in a layered soil system. Different frequencies will travel at different speeds. And those speeds and frequencies are all linked together in the equation that says that velocity is equal to frequency times wavelength. It so happened at that time in Salzburg, Austria, some excavations were being performed to repair the floor near the main altar of the cathedral. And those excavations revealed that that cathedral, built in the 1100s, was not positioned over the original cathedral of the 900s. What had happened? Well, it turned out that the engineers did not understand the precession of the Earth's axis, and therefore the change in north in the compass directions. So the new cathedral was built along a line set out by old methods, and the main columns did not fall over the main foundations.
Oh, wow.
Fortunately, the ground was good enough to carry the loads, but of course the question was, where are the old foundations? Professor Prange from Karlsruhe suggested that we explore the region using Rayleigh wave dispersion, which in fact we did. We took a 300-pound force electromagnetic vibrator to Salzburg, and we ran lines of Rayleigh wave dispersion, and at some places the contour lines describing wavelengths was deformed, deflected. And at those locations, we dug down and found the foundations. In fact, the cathedral had been built 9 degrees off from the line that they thought they were on. But this technique requires that you set a vibrator in motion at a given frequency and then find the in-phase points of the Rayleigh wave moving out from the source. Then you had to change to another frequency because that would sample a different depth, sampling approximately equal to 1 wavelength deep. So you had to run the same test essentially many times. I did that for my thesis in looking at the effectiveness of trenches. Well, at Karlsruhe, they had a fortuitous arrangement that within their geotechnical group was an electrical engineer. And the electrical engineer looked at what we were doing and said, well, if instead of steady state vibration, you create an impact, the impact will have many frequencies. All you have to do is sort them out. There was the stumbling block. How do you sort out the frequencies? In 1977, we had a major engineering conference at Karlsruhe looking at soil dynamics and earthquake engineering. At that conference, the electrical engineer, whose name was Ressler, demonstrated the use of a very sophisticated 2-channel FFT, Fourier transform analyzer. The analyzer at that time took up most of the space in a Mercedes type a Jeep. So he had this equipment in the field and electromagnetic shaker and a sledgehammer. And he demonstrated that he could collect the data from a string of geophones placed on the surface of the ground, and he could determine the wavelength for each frequency. Now, this was a cumbersome set of instrumentation. Well, that demonstration then piqued our curiosity, and Ken Stokoe picked up on that, and I'll get back to that part of the story a little later. But that was sort of the key to unlocking the technique which has become spectral analysis of surface waves and multi-analysis of surface waves. So, of course, as a young assistant professor at Michigan, we were expected to perform new research different than our thesis, and of course find funding to cover it. I was fortunate enough to learn about the process called holographic interferometry. This process allows you to take holograms. Hologram is a picture of sort, but it has three-dimensional properties to it. I learned from the electrical engineering department at Michigan how to use a laser to create holograms. And based upon learning that process, I was able to obtain National Science Foundation funding to perform model experiments on wave barriers. And in this case, I did use both filled and open barriers. So for the next 5 years, I was funded to study the effectiveness of trench barriers for reducing ground vibrations. And we published several papers on the application of holographic interferometry in soil dynamics. We confirmed all of my earlier conclusions with regard to the effectiveness of trenches, and extended to other possibilities. Specifically, it's hard to keep a trench open, say, to a depth of 50 feet with nothing supporting the walls, if you don't fill it with something that, some material which eventually becomes rigid. So we tried again the material that Dalling had used in Germany, and with the same sort of results, that those bentonite slurries eventually became rigid unless you stirred them. Okay, you could put a mixer down there, but how close did you have to put the mixers to keep a significant length trench? Significant length meaning at least 100 feet, maybe 300 feet long. That didn't look too promising. So we looked at other things, concrete and metal, and we could do this because we were working at the model scale. Our model half space was 1 meter in diameter and about 30 centimeters thick, and it was just a clean, uniform sand. But getting back to my story, it's hard to keep a trench open. But a cylindrical hole is a little more stable. And besides, we know how to make cylindrical holes with very thin walls. That is, we have available, and at that time they were being used for producing piles, corrugated thin wall sleeves. They'd be driven with a mandrel and used for pile, but these same sleeves then could potentially keep holes open. Therefore, in this model's arrangement with the holographic interferometry, we studied rows of holes. First of all, a line of holes with different spacings until we found a spacing that was sufficient to almost mimic an open trench. And then to get closer to the open trench effectiveness, which was our gold standard, we put in a second row, with the second row of holes filling the gaps in the first row. And with this scheme, we were able to come very close to a open trench condition. And we established a guide that related the diameter of the cylindrical hole, the spacing center to center of the cylindrical hole, and its effectiveness relative to a empty trench. So our effectiveness ranged from a value of 1, which was the best, to, well, in our case, we were down to about 20% effectiveness. It was many years before that concept was tested. We'll get to that also later. Of course, during these early years, on the assistant professor at the University of Michigan, I was teaching foundation engineering and occasionally soil dynamics when JohnRHall or Bill Richart didn't teach it, and developing other courses of my own, including a course in tunneling and in marine structures, waterfront structures. And the work on the waterfront structures was triggered mainly by the federal funding of marinas for essentially recreation in particular, and many marinas being established around the Great Lakes. So there was a strong interest in that. And of course, marinas in the Great Lakes come with the winter frost problem, and we learned about the ice jacking of piles. That is, as the ice formed around piles and the ice got thicker, the ice would pull the piles out. And we, along with colleagues at University of Wisconsin, developed criteria for how deep you had to embed piles to prevent their being jacked out by the ice in the winter. So that was the thrust of my work during the first 10 years on the faculty at the University of Michigan, bringing us up to about 1980, and a number of graduate students in that era who carried on some important research. I don't remember which students overlapped at the time, but there were some important discoveries at that stage. One of which was the determination that very small amounts of air dissolved in water would change the wave propagation in water. The graduate student who performed that research, by the name of Neville Allen, learned the chemistry of water to the extent that he built his own device for measuring air content. And This was a rather sophisticated blown glass equipment which he would manually spin to get the centrifugal effect, and with this process and the physics behind it, he could determine the air percent in water. Well, his experiments coincided with an era in which the U.S. Army Corps of Engineers was examining the seismic stability of earth dams. Professor Richart had a contract with the Waterways Experiment Station with other colleagues here at Michigan, Professors Ben Wiley and Victor Streeter, to evaluate how you can determine the safety factor of slopes of earth dams, particularly those dams which have fluctuating pond levels, where the water is used for irrigation or for other purposes, and the elevation of the lake changes. Well, one way to examine the water infiltration into the face of a dam would be through propagation of seismic waves. P waves in particular, because the P wave would propagate through saturated material. The thing is, in field tests, the Corps was finding that the velocities were not 1,500 meters per second. They were less than that. Richart combined his knowledge of Neville Allen's thesis with those results and concluded that the fluctuation of pond level changed the degree of saturation in the slope, and that you could tell the degree of saturation by the P wave velocity. That the P wave velocity did not attain 1,500 meters per second until the water and the air in the water reached 0.999% saturation. Anything less than full saturation produced lower velocities.
99.99.
Yeah. It might be interesting to note what our student body was like in the geotechnical and specifically soil dynamics area. From the mid-60s onward, we generally had at least 2 students working on their PhDs. The National Science Foundation fellowships ceased about 1970. So we didn't have those any longer, but various of us had research projects that supported students. Our master's student body varied, probably between 5 and 15 students at a time, until the mid-70s. During the mid-70s, Bechtel Corporation opened an office in Ann Arbor and had a large number of employees, over 1,000 employees here.
Wow.
And during that, the first 5 years that Bechtel was in Ann Arbor, we had master's classes that would be well over 20 students. And because of the number of students and the location at which most of them worked, we taught the courses in the Bechtel building.
In Detroit.
Both Don Gray and I went out to teach those courses. It seemed like there were always clusters of students that seemed to provide a strong nucleus. In my first experience at Michigan as a student, it was VincentDrnevich and myself, and Sharif Afifi. Then a little later we had Don Anderson, Ken Stokoe, and a master's student who went on to Berkeley, Mike Katona. And we formed a very strong group with those students. And later, we'll talk about later groupings, but I'd like to drop back to mid-70s again. Professor Richart was contacted by his friends and colleagues at the consulting firm Tibbet, Abbott, McCarthy, Stratton. It's called TAMS. They were the designers of the Tarbela Dam in Pakistan. They had some serious problems, some accidents, and these led to their looking into the dynamic response of structures, appurtenant structures, and the dam itself. Bill Richart was contacted by John Lowe, who was the principal in charge of the Tarbela project. And that resulted in my going to Tarbela, and in the first summer of '75, working with Arthur Casagrande on the issue of sinkholes developing in not only the face of the dam, upstream face of the dam, but also in the permeability blanket that was established upstream from the dam. In the blanket, many, maybe in the order of 20 sinkholes were identified. They could be fairly easily filled once the water was back up again, and they could dump from barges and so forth. One major sinkhole occurred in the upstream face, and that sinkhole was excavated to observe how deep it went. And as a young, the youngest engineer on the site, Arthur Casagrande, sent me down to crawl among the facing blocks to see how far I could go. And so I, maybe a meter and a half down in between these large facing blocks. Now, they've later excavated deeper than that and pretty much confirmed that Arthur Casagrande's design approach, that being coarser materials near the surface getting finer and finer, worked as a reverse filter that trapped materials attempting to flow through the dam and stopped further erosion along that line. So a fairly extensive study was done at the upstream sinkhole to well establish that the Casagrande method had worked nicely. Other things occurred, though, during that era at Tarbela Dam. There was a major accident that occurred when a gate to a irrigation tunnel got stuck in an open position, and it resulted in washing out of a portion of a 45-foot diameter tunnel and erosion of many thousands of cubic yards of soil at the upstream face. The issue associated with that accident that Professor Richart and I looked into were the vibrations. What vibrations did that cause? And there were two main structures that were influenced, and they were the gate structures at the lower end of the tunnel, at the outlet end of the tunnels, and the gate lifting equipment at the top of the dam. There were total of 4 tunnels. Only one of them was damaged in the accident, but that caused shaking of the gate structures. At later dates, after the failed tunnel was repaired and the elevation of the reservoir could be adjusted, we made other vibration tests on the gate structures with various flow conditions. And for most conditions, we found that the structures were well designed with no hazard. On the other hand, the gate lifting equipment along the crest of the dam over the tunnels was more vulnerable, and the main hydraulic cylinders were in need of some reinforcement to make them secure and safe from internal vibrations. The biggest challenge, however, was in additional subsequent to the initial design, seismic analysis. They wanted to know the upstream, downstream natural frequency of the dam. The dam is nearly 2 miles long, 460 feet high. How do you determine the natural frequency? Well, we established measurement stations at the center of the dam, at the crest and at the toe, and at the third points at the crest and the toe, downstream toe, and instrumented with low frequency geophones these 4 sites. Then we excited the dam by flowing water through one of the tunnels. And it turned out that the calculations made by Professor Streeter at the University of Michigan was that the organ pipe vibration of the 45-foot diameter tunnel, about 1/4 of a mile long, would be on the order of 1 hertz. So with water flowing at different depths through that tunnel, we obtained different frequencies for the tunnel until it was flowing full. And so we went through the first mode natural frequency of the dam into slightly beyond. Furthermore, determined that the crest amplitudes, upstream, downstream motion only, were 4 times the toe values. So there was a slight amplification in the ground motion. And by the way, the tunnel elevation was essentially at the toe elevation of the dam. So these were important observations, and it was a thrilling experience to participate as a young engineer at such a major project. Tarbela Dam consists of an earth and rock fill of 140 million cubic yards. It remains as the largest designed earth embankment in the world. There are larger tailings embankments, but none designed for a specific engineered dam.
So that project is, you interacted with Arthur Casagrande in this one?
Arthur Casagrande was a consultant to TAMS. On a project that large, there are a number of participants, and besides the design engineers, there were 2 sets of other engineering firms, one in London and one in Chicago, who were looking over the shoulder of TAMS and checking their designs and well, anything associated with the dam. The Tarbela was promised to the Pakistani people at the separation of India and Pakistan, I think it was 1948, and the United Nations pledged help to Pakistan to build a dam on the Indus River, and pledged to help India, and they built the Mangala Dam. I'm not going to remember the name of the river. Well, that was the Tarbela Dam was completed in the late 70s and has functioned since then. It was initially designed for irrigation, power production, and flood control. The irrigation operation did not turn out as satisfactorily as expected. It was hard for them to change the farming operations. So that function, while still has some usefulness, the power generation is the major result of the dam. The reservoir is quite significantly silted up at this stage, but still provides a good elevation difference for power production. So its irrigation mitigation capabilities are lessened.
Did you interact much with Casagrande on this project?
No, just a few days associated with that sinkhole. Unfortunately, it'd been nice to work with him more, but it was fun just to be out there on the site at the time.
Awesome.
Now, I guess I've got to think about where we go from here, because we're sort of, I've talked about the 1977 Karlsruhe conference.
Yes. So when did Richart come to the department?
Oh, well, Richart, of course, was already here
When you came?
when he invited me.
Yes.
He had come from the University of Florida in 1962. He had been on the faculty as a professor at the University of Florida, and was recruited to come to Michigan as the new department chair, with the expectation that he would build the department with more heavily along the academic lines. In other words, PhDs.
I see.
And he did that very successfully.
So he served as department chair from when he came to how long?
Until 79,
Oh, a long time.
when GlenVBerg became chairman.
I see.
GlenVBerg was structural faculty member.
So he was department chair at the same time with all the work on the soil dynamics, huh? He was
That's
doing
right.
both.
That's right. Extremely busy man, but very successful.
How was soil dynamics perceived at that time? You know, like you mentioned that only Michigan and primarily Michigan and MIT were doing work in that direction. Was it considered like an important topic, an esoteric topic? And what is its relationship with the earthquake engineering too?
Well, the soil dynamics got its impetus from the DEW line. The DEW line was the distant early warning radar lines across North America, whose intent was to give early warning on Russian bombers coming over the poles.
Uh-huh.
And the Corps of Engineers was assigned the task of at least advising on the design of foundations for what at that time were the most sophisticated radar antennae available. The foundation design was totally unknown. Coincidentally, along about the same time, offshore structures were being built to explore for oil, mainly in Southern California and then in the Gulf of Mexico. These two things together drove the need to know about foundation dynamics. And I think my first recollection of these two coming together was at a MIT conference in summer 1960. And at that conference, both RobertWhitman and Bill Richart made presentations on soil dynamics, and things were taking off at that time. Now, I retrogress a bit here because associated with this question is some of my earlier history. I graduated with a baccalaureate degree in civil engineering from Notre Dame in 1957. And while I was doing my college work, I didn't want to be in ROTC. I could see the time that it was taking up, but there was a program in the Marine Corps to train officers, and it used only summer weeks. So I became a recruit in the platoon leaders corps in the U.S. Marine Corps. So after I graduated from Notre Dame, I went into the Marine Corps and was assigned to Engineering Battalion. Got some training on the East Coast in Camp Lejeune and was sent to Pendleton, California. Well, I was assigned to Engineering Battalion there, but within a few days, an order came from the base commander asking me to report to somebody for an interview. And I got to the interview, and they said, "You have a civil engineering degree?" I said, "Yes." And they said, "Well, you must be a hydraulic engineer." I said, "Well, not specifically, but I studied a little bit of that." So they said, "Well, we're going to transfer you out of the Fleet Marine Corps into the base commander's offices." So from that day forward, I was listed as a hydraulic engineer, and I prepared documents for a water rights litigation. Camp Pendleton in Southern California is astride the river called the Santa Margarita, and the Santa Margarita goes on upstream as far as Mount San Jacinto, Hemet area, if you know anything about Southern California. In that region is the United States primary avocado growing agriculture. Avocados take a lot of water. And so the growers were extracting the water from the Santa Margarita River, and nothing reached the Camp Pendleton at the surface. There was some underground, but at the surface. So in any case, the Navy, of course, owns all of the Marine Corps real estate. And so the Navy sued the Avocado Growers Association for extracting water from the Santa Margarita River, which would be riparian rights to the Navy if it came through the Pendleton. Well, the suit was started a couple years before I arrived, but we were right in the throes of doing and creating evidence for the court. Well, the judge hearing the case, recognizing the multiple landowners in the Santa Margarita watershed, and their resources were generally limited, that the Navy should provide engineers to make assessments of each property that requested it. So that was what I was engaged in, measuring water wells, how deep were they, what was their discharge, using weirs and channels to determine water flow and so forth. And so for 2 years, more than 2 years, that was my job in the Marine Corps. I'll have to brag a little bit. During that time, at least, I went to my annual rifle and pistol qualification, and I qualified expert both times, or every time in both weapons. I did spend a little time too on the base open sight rifle team, and we shot at human-sized targets from 500 yards. Almost 500 meters, which is a pretty long shot. Yeah. Anyway, my experience at Pendleton piqued my interest a bit in hydraulic engineering. So when I completed my Marine Corps experience, I decided to go back and study hydraulic engineering. Just to back up a little bit, I convinced the Marines to send me to that MIT conference where Whitman and Richart were talking.
Wow.
That didn't turn me around to soil dynamics yet. I was still hydraulics.
Oh, but you were there. Wow.
I was there, yeah,
Wow.
as a Marine officer. And
Did you know Professor Richart then? No.
oh no, I didn't know him from anything, and just saw his talk and thought, okay, that's good. But I examined a number of possibilities for a master's, and because they had my record at Notre Dame, they said, okay, you can come back and do a master's, and for your tuition and a livelihood, you'll teach surveying. So I did, and so I started in hydraulics, and I took a couple of interesting courses, but the professor in soil mechanics really attracted my attention. He had received his education at Purdue when Philip Rutledge was on the faculty at Purdue. And he did so many things in soil mechanics that I said, well, I'd like to learn a little about that. So I kind of switched from hydraulics to soil mechanics due to my master's level geotechnical engineer, Professor Leroy Graves. And so that got me into soils. Well, at the same time, at Notre Dame, the department head, his name was Harry Sachs, and he was an MIT graduate, and he was in the era where many of their students were supported on secret contracts. He couldn't even read his thesis at Notre Dame. It was back in Cambridge, Massachusetts, and he'd have to go back there to read it because it was classified. But of course, he knew some things associated with it. So along with the soil mechanics, he kind of was trying to push me into soil, earthquake engineering, but more specifically, nuclear effects. And the nuclear effects dealt, as far as he was concerned, with cratering. So I completed my master's at Notre Dame, and through Professor Sachs, he got me a fairly high level job at the Air Force Weapons Lab in Albuquerque, New Mexico. And the Air Force Weapons Lab dealt with the design of underground protective structures, tunnels and silos. And so I was a bit familiar with dynamics when Richart interviewed me at University of Michigan. By the way, I went to Michigan Tech along with one of the other civilian employees of the Air Force Weapons Lab, GeorgeYoung. George went up as department head, and he took me along. Since I had a master's, I only was a lecturer, but that's how I got to Michigan Tech. And I was only there a year, after having been at the Air Force Weapons Lab only a year.
Wow.
So I moved from general civil to hydraulic engineer to soil mechanics. And it was soil mechanics in those days, not geotechnical engineering. Anyway, now you ask, where did Richart and Whitman fall with regard to soil dynamics, and what was the view? Of course, Whitman and Richart had already begun their investigations, research into soil dynamics, machine foundations, radar towers, offshore structures. late 50s, early 60s.
Okay.
And it was the 1964 Great Alaskan Earthquake that pulled Harry Seed into the picture. Harry Seed started investigating or did major investigations on the Anchorage earthquake. Turned out they both needed the same soil properties. Whether it was earthquake engineering or machine foundations, you need to have shear modules. And so that was sort of the unifying effect of the earthquake. It brought these groups looking at the same kinds of problems. And then JohnLysmer, after his completed his degree at Michigan, moved on to Berkeley and then worked with Harry Seed in earthquake engineering. And there were, at that time then also came along the nuclear power era and the design of nuclear power plants. And Harry Seed and his colleague Ed Idris in California were devoting part of their time to earthquakes and part to nuclear power plants, and a lot of East Coast work being followed by Whitman and Richart. The Bechtel Ann Arbor office was populated in the late 70s for the nuclear power business, and I explained a little bit how that influenced our student body, particularly with a lot of master's students coming available. One of our early PhD students, Sharif Fifi, became a group manager at Bechtel at that stage. He was working on the, particularly on the Midland, Michigan nuclear power plant. Okay, now where do we go?
I think we can have a pause here.
Yeah.
It was interesting, but there was so it sounds like there was an interesting cross-fertilization with having Lysmer going from here to Berkeley.
Absolutely, on purpose.
And I heard a lot about Lysmer when I was there.
Yeah.
About the influence he had over there, and so it sounds like, you know, I actually hadn't at that time made the connection this was Michigan related.
Okay.
So
yeah.
it's very interesting.
Yeah. Well.
Interesting.
John was an interesting guy, sometimes difficult to get along with, but socially he was very, a very nice guy to work, to talk to. I took one course with him, and he tended to talk to the blackboard and mumble.
Really?
And so he was a little hard to understand, but it was really a mathematics course.
Really?
It had very little to do with soil dynamics.
Interesting.
But of course, they were the tools necessary to go on. And the story that John told about himself when he started lecturing at Michigan while he was doing his PhD. He said, for a long time, I would look at my students and they looked so puzzled. I would write something on the board and tell them about this, and I thought it was pretty clear. And said, finally, one of the students told me that they didn't know what equations were. So John did a lot. of course, his native language was Danish, and so he had trouble with some words or expressions, and that was one of them.
Awesome. Very interesting. Thank you very much.